Hello guys, Assalamualaikum warahmatullahi wabarakatuh and a very good morning. So today we're going to talk about more on the optimization tool, which is response surface methodology. So by having the DOE designs of expert software, you can run your experiment. You can choose either you want to do response surface methodology, you want to do optimal, or you want to do box backend. You can choose the type of model. So it's important for you to understand the ability of your material. Is it you can set the range to the critical value, to the minimum, and also to the far maximum? Then you can go for response surface methodology. If your parameter just circulate into certain what we call the range, you cannot go to very far minimum and far maximum, you can go for box backend. If you want to determine your parameter itself, for example, certain concentration you need to put the value, go for optimal of optimum. A lot of design have its purpose in the DOE. Enough with that. So let's talk about response surface methodology, because most of the cases we want to study either the material can go beyond minimum critical value to maximum critical value. So you want to determine is it the capability of your material can go at critical condition. So depends on your parameter. So normally what we did, if you do 2 parameter, you can get around 13 to 11 set of experiment. If you have 3 repetitive value, you only have 11 experiment. If you have more, for example, you have 5 repetitive value, then you can have around what we call that 14 or 15 set of experiment. So it depends on your repetitive at the middle point. So what's important is for the ANOVA, you want to determine number 1 is the model is significant. The model you can choose from the software. Either it can be quadratic model, it can be linear model, it can be cubic model. So a lot of model is there. It can also be reduced into square root or log of the model. So you can choose type of model. So it's important for you. Normally if you have 2 parameter, goes for quadratic model. If you have 3 or more, cubic model is better, but sometimes it's also fit for quadratic model. So that's number 1, choose the correct model, either quadratic, cubic, linear, and so on. Okay, so in the ANOVA you have a subset of the model. If you choose, for example, quadratic model, you have model term A for parameter A, model term B for parameter B. This only specific case for 2 parameter. So if you have independent parameter A and parameter B only, you have model term A, model term B, model term A, B to see the correlation between 2 parameter, and model term A square and B square. The model want to see what happen if they multiply by 2. Square root of your model, what happen? Is it the p-value stay less than 0.05 or increase? And it is important to determine the p-value. Normally the software determine for you. If the p-value less than 0.05, your model is significant. Okay, so then out of 5 submodel A, B, A square, B square, you should have majority of them is significant by having p-value less than 0.05. If only 2 significant, it's also okay. So, but you need to justify why the insignificant of the rest of 3 model. The more, the better. But if 2 or 3 is significant, it's okay. You can justify actually. Okay, next, from that, you want to determine the R square adjusted, R square predicted, R square. So for a layman, difficult thing becomes simple. The R square adjusted, R square predicted, R square should close to 1. Depend your application. If your application is based on material science for chemistry, energy storage, It's quite easy to get the R square close to 1 if your outcome similar to the outcome predicted by the model. If you are dealing with biological, you are dealing with environment, it's quite difficult to get the R square close to 1. So depending on your reference, your published journal, you can see what is the range of the R square. Okay. Enough with the ANOVA analysis, we go to the optimization. Okay, in that software, you can choose the optimization. Okay, to do the optimization, you just click the optimization tab, goes for the solution given, and you can do two ways. One way, you pick 3 solutions and try to run the experiment and get the expected surface response compare with the predicted surface response. Then you calculate the residual standard error, RSE. Okay, that's number 1. Number 2, just choose one solution and repeat 3 times. In this case, you can do the optimization or validation test. The other one, you can do repetitive test. Okay, 2 in 1. The same thing, calculate the residual standard error, then you can prove how much the percentage your model capable to predict your surface response based on the optimum value suggested by the model. Okay. After that, finish with the ANOVA and also optimization test. Now you carry forward to the graph. What graph should you highlight? Because when you running the DOE, a lot of graphs appear. You have a constraint graph, you have a box graph, box score, and so on. So first, the number 1 important graph is about the percentage error distribution versus external standardized data. Okay, so you want to see if your error is normally distributed. So that graph is important, but some paper did not include. It's okay. So that graph want to see if you have heavy tail or heavy head. If your data lies on the straight line, means that your data is good. Means that the error is normally distributed. That's number 1. So number 2 is predicted versus actual. So to see, did the model predict accurately? For example, your surface response is very capacitance. So did the model predict 100, you get around 98. So means that the model capable to predict 98% depending on the theoretical data and calculation. So that's important. Again, we want our data lies on the straight line to increase the efficiency of the model. Then the third last is about the 2D and the 2D graph. Okay, from the 2D graph, you want to observe the shape of the contour, because 2D graph show the contour between each independent parameter to the surface response. If your shape is eclipsed, means that your independent parameter significantly affect your surface response. Okay, depending on the shape of your graph. Then you can read more journal, a lot of shape of the contour graph. Eclipse, round, and non-eclipse. So you can observe the behavior from that. And a very interesting about the response surface methodology is we're going to talk about the 3D graph. Okay, 3D graph is quite good. The graph is amazing. So it looks beautiful. So from the 3D graph, you can see the correlation between each independent parameter to the surface response. You can see the curvature. If your subset model is significant to your surface response, if it's not significant, p-value more than 0.05, you can see almost no curvature. It might be flat, it might be linear, no curve in your graph. So the more intense the curvature, the more strong interaction between your independent parameter with the surface response. And last but not least, before you skip the graph, the other graph part, it is important to know either you put the one plot factor or the perturbation plot. Perturbation plot is important to see the correlation between these two independent parameters towards surface response. Because you study the two independent parameters simultaneously. In this case, two parameters. If you have three parameters, you study three independent parameters simultaneously. So perturbation plot is important to see the behavior between each independent parameter towards each other. So it's important to do that. Then after that, enough. You already got your full optimization with response surface methodology. A tricky part during the experiment, you might observe, first of all, your model is not significant at all. You need to repeat maybe the first thing first. What happens if your model is not significant at all? It might be your range is not suitable. That's why you need to do a very good range by having a preliminary experiment. Number two, what you can do if some of your experiment give non-significant value, you need to repeat some set of experiment. That's number two. And number three, make sure the R square is good. If the R square is negative, 0.1, 0.2 is not good. You need to see from your set of experiment what is wrong. From the model, they will tell you which number of experiment is wrong. Sometimes you can just exclude that number of experiment. Sometimes you need to repeat and see the problem. Because we are human, we make a mistake. That's why we need to track back what is our mistake. So I think that's all about response surface methodology, about the optimization tool. I hope you're interested. Okay, bye. See you again.